I'm going to talk the basics of the capacitors, and I'll move to the MOS capacitor. Okay. So the basic title is this. MOS capacitor is my title. That's what I'm going to present today. So under that, I'm going to talk with this plan. Okay. So as Dr. Prakash said, if you have any questions, you can interact in the middle of that also. Okay. So I'm going to introduce you to the capacitors, which are normal capacitors that we have studied in our master's program. And there I explain what is the working principle of the capacitor and why we need to have the capacitor, and how you can charge it and how you can discharge it. And later on I'll move to the MOS structure, which is also similar to that regular capacitor with a slight difference. Okay. So their complete phenomena is depending on many other different factors that we will see them one by one. And all these MOS capacitors are built on the basis of the thin films. Okay. So thin film technology is important to be known to understand the fabrication of MOS capacitors. So I will slightly touch this part, the thin film part also, and some techniques to deposit the thin films also I will explain. So after that fabrication, I will move on to the, studying the MOS capacitors. Sometimes I use MIM, I'll tell you the difference later. I put just like a microscopy of this, but it's not just the microscopy. Once you deposit the films, you need to understand the films. So that will tell you what type of coating you have done, all those things. Okay, so that I will tell you that. And I'll little bit talk about the current technology, and that is kind of materials that are being used in this MOS capacitor later. Okay, then I'll conclude. Okay, yeah. So in the introduction part, capacitor, we know this. I'll go to the writing mode because you're all the regular students. I prefer to write on it with different colors maybe. Okay. So, so the capacitors, when we talk about, we know that it is a passive component. Okay. So in electronic components, you know that one is an active component that does some function or that shows a gain. And some of the, components which are passive components, which works, but, it will not be having any gain, like a transistor. Transistor is an active component because that amplifies the signal. But these passive components will do some function, but it will not amplify. So they are all called as passive component. Okay. And it finds a lot of applications in many types of electronics as well as in electrical. Okay. Even if you look at the fan, for example, if the fan is not running smoothly or fastly, immediately the electrician will come and say the condenser is gone. Or if you look at the AC unit, air conditioning unit, they say the condenser is gone. A condenser is nothing like a capacitor, which is storing an electrical energy. Otherwise, it works like a battery, but it's not exactly the battery in the working methodology, but that stores energy, and this has a capacity to release the energy in a very fraction of a second, very quickly. Okay, some inducting coils which needs heavy energy in a fraction of a moment. When you want to have that, the capacitor which is already charged, when you switch on the fan motor will be immediately activated by the release of energy from the condenser. That's what it does. And it is not just only that. There are many applications. Okay, filters and, oscillators and many of the electrical circuits, we use them. Okay, so that's why the capacitors are very important component of the electronics and the electrical, and we have to understand that. So based on that, I'm going to talk about MOS. MOS stands for metal oxide semiconductor capacitors. Again, these are all capacitors. Okay, MOS device people used to say. Otherwise, it's metal oxide semiconductor capacitors. Okay, which is the core for VLSI technology. You know about that, right? Very large scale integration. for the fabrication of the ICs. They use this, and this MOS is the base for all the MOSFETs, FETs, field effective transistors, field effect transistors, right? So all of them are based on the principle of this MOS capacitors. So that has to be understood, and that is the objective of this talk, okay? So here MOS capacitor will be discussed with metal and semiconductor components which are separated by an oxide layer. I will talk about the structure, then you will understand very clearly, okay? Then you see, I'm not going to just talk about the MOS capacitor. See, there are very special characteristics or very important parameters are there for these MOS capacitors, and one of them is thickness of the oxide layer. Okay, we will see that, and flat band voltage, flat band capacitance, and doping profile of the oxide layer or the semiconductor. All those things we should see that, and we will see them. Okay, so that is one layer is called as an active oxide layer because it's metal oxide semiconductor. This oxide layer is the one we use as an insulator. In a regular capacitor, you have an insulator in between the plates. So here, this oxide material are being used as the, it's like an active layer, which is a very important layer in the MOS device. So that has to be studied actually, and that determines or dictates the quality of working of this MOS capacitor. So that we will be studying a lot actually, okay? Especially, it says that chemical composition. For example, one material which is very popular is hafnium oxide, okay? Hafnium oxide can be used as an active layer in a MOS capacitor. And when you deposit hafnium oxide film, and you should understand what type of oxide it is, which is like, it's an amorphous, crystalline, or what phase it is, or it's completely stoichiometric or non-stoichiometric. All those things you need to understand so that we will see that, okay? So, so basically when you need them as a film, I will talk a little bit about the deposition of the layers on the device, okay, to fabricate the device. So that's one area. So I'll talk about a little bit about the deposition techniques also, okay, thin film deposition. Actually, I do not know how to hide all these. Maybe I can hide all these videos. Yes, I have. I don't see my slide by myself. Yeah. So this is typically the capacitor I'm going to talk about here. Okay. Capacitor, we know that, right? Capacitor, it's an electronic device that is used to store the electrical energy. Okay. See, batteries also used to store electrical energy, but battery is able to produce electrical energy from the chemical energy. Okay. It is also storing energy, but it's completely different. So capacitor, in a way, you can compare it with the working of a battery, but it's different actually. Okay. So capacitor is the electronic device used to store the electrical energy. That's an important point. How it stores, we will see that. Okay. They are only used to store the electrons or the electrical energy. Electrical energy is nothing but electrons, right? Because if the electron flow, you get an electronic current. So that's what we want actually. And they're not capable of producing them. You see, in a capacitor, if you have the capacitor is not able to produce them, but they can store them. Okay, so that's an idea. But in the case of battery, if you compare this with a battery is able to produce electrical energy from the chemical energy, and also it can store them actually. Okay, so I will tell you the differences if somebody asks you later, but there are things. Okay, so what is in the picture is the basic structure of a capacitor, in which this layer is a metal piece or the metal electrode. Okay, and same type of metal electrode is kept at the other side also, bottom. But these two metal layers or metal plates sandwiches a material which is a dielectric material or an insulator material with a thickness of D. So that's what is given in an orange color here. Okay, so that is exactly the parallel plate capacitor that we usually study there. Okay, so two metal plates separated by a insulating layer. Insulating layer can be air also many of the times, but if you want, you can use proper materials like different organic or inorganic, even liquids can be used. Okay, so this is the capacitor. So when you connect capacitor with a battery, here is in positive polarity and here is in negative polarity. When you connect them, actually, this from here onwards, this electron starts to being pulled by this, because this is a positively charged one. So electrons will start to flow this way. So electrons are coming this way and it is going towards the here. And this one is a negative terminal which supplies electrons to this electrode. Okay. So here electrons are being pulled away. So for every electron is extracted from this electrode, this will become positively charged. You can directly also say we are giving positive charge, whatever be it is. Okay. So you are charging the electrode here. And similarly, you are supplying here electrons in this way. And so this side is becoming more negative here. Okay. When this capacitor is connected to the external supply voltage or the battery, which removes electron from one electrode and supplies electron to the other electrode, so that one side will become positively charged and another side is becoming negatively charged. Now, when there is no applied voltage, there is no charge actually. This is not built there. It's completely neutral, and this is also completely neutral. Only when you start supplying a voltage here, and here positive charges started building up, here negative charges started building up. So completely, you look at that. Now, the uncharged electrodes become charged now. Okay. So now let's say that you're removing it actually. You take this battery out. Even if you take the battery out, these charges will not be released, which means the first cycle I will call it as a charging the capacitor, which was charged. Then later on, this capacitor will not discharge by itself. Okay. You charge it and take the battery out. And if you want to store this, in a proper, design and just, it should be manufactured. I'm just saying by words, but there are many types of capacitors. I don't have the image here, thinking that you know what the capacitor is. So if you leave the charges, it can stay in here for, I don't know, maybe years and years, maybe tens of years. It will not be discharged by itself. If you want to discharge it, what you should do, you have to connect some load here. Okay. If you connect a bulb, for example, if you connect here and these charges will start to flow again from here, from this negative side to the positive side, electrons will flow and the bulb will start to glow there. As long as the charges are there, the bulb will glow. And once the charges are completely neutralized, when electron comes here, kills one positive charge. Like that, it will be neutralized. Discharging is taking place. So when it completely discharges, it will become neutral and the bulb will not glow. You need to charge again. That is the nature of the capacitor. Okay. Once you develop charges here, because here is a positive and here is a negative, there because of the charges, two charges separated by distance, then if you take, there an electrical potential will be developed because of the charge separation, and that charge will be, that potential will be V. So according to the V, and it will develop a field E, which is defined by V by D. Okay, otherwise del V by distance. Okay, that is what the thing is. So electric field is developed this way, but the charges cannot flow through this. Why? Because this is an insulator. If you have a conducting medium in between, charge will just go through, and there will not be charge build up here. Because of the dielectric layer, these charges will not diffuse into this, so that the charges once deposited or charged on the plates will stay there as such. Okay. So these are all the, field will be set up there. And once you have the capacitor, and we should be talking about the capacitance. Okay. What is a capacitance? The ability of the capacitor to store charge. If the capacitance is more, you can say that it can store more charges. And if the capacitance is low, you can say you can store very less charges. Okay. That is defined by electrically by this way. Capacitance is equal to Q by V. Otherwise, the total amount of charges per unit potential or unit applied voltage, which is, when you apply a voltage, there is a quantity of charge which is built up there. So when you divide that by the applied voltage or the potential developed here, and that is called as the capacitance. So Once you know the capacitance, and the capacitance needs to be measured, and the unit to measure the capacitance is farad actually. Okay, if you want to define 1 farad and 1 farad, you have the, how much actually, okay, otherwise the 1 farad is the capacitance. If the stored charge is 1 coulomb, charge is 1 coulomb for 1 volt of applied potential. If you apply 1 volt to the capacitor, and it should build 1 coulomb charge in that, and that is called as, in that case, the capacitance of that capacitor will be called as 1 farad. Actually, farad is quite big unit. Normally, capacitors will be having a millifarad or microfarad. Okay, microfarad is very common, that normally being used in very regular electronic circuits. Okay, so this is an electrical way of defining the capacitance. There is another way of defining the capacitance, which is geometrical capacitance. For example, the C, which is capacitance, is defined by epsilon A divided by D. D is the thickness of this layer, or the distance between the plates, whatever it is, because the dielectric material is sandwiched between them. The thickness is going to be exactly the same as the distance of separation between the plates. Okay, area is the area under the area of the plate, the cross-sectional area of the plate. Okay, and D is the distance, and epsilon is the dielectric permittivity of the material. And the dielectric permittivity again can be defined by epsilon naught and epsilon r. It is the dielectric constant or permittivity of free space or air, and epsilon r is the relative permittivity of the medium actually. Okay, which is the dielectric material which is kept here. Correct? See, so here look at that, and here also we can talk about that. If you want to increase the capacity, if you want to increase the capacity, what we should do here, you should apply more voltage, because when you increase the voltage here, and the amount of charge which is built up is also more. So if you want to increase the capacitance, the one way is to increase the applied voltage. But you cannot keep on applying voltage to infinite, so that infinite charges can be stored here. That cannot be, because every capacitor has a particular rating of voltage. If you go beyond, there will be a dielectric breakdown, and this dielectric will break, and the capacitor will blast actually. Okay, so that won't be happening there. But another way here, based on this expression, the capacitance can be increased, because the capacitance is directly proportional to epsilon and area, which means that you can either fabricate a capacitor with a smaller dielectric, smaller plate, or larger plate, or even larger plate. So when you increase the area of the plate, then your capacitance will be naturally increased, because you have a lot of area for the charge to accumulate. So naturally your charge accumulation will be high in that case. Okay, and also you can, this capacitance is inversely proportional to the D. That is the D here, distance between them. This also you can decrease as small as possible. Okay, when you have them very closer and you have higher capacitance. But you cannot go very much smaller. There is a limit actually. If you go very closer here, then the charge here and the charge here will not stay, because there will be a tunneling possible, and this charge will start to leak through the dielectric layer, and it forms a current that's called as a leakage current. That also will be happening there. So the dielectric material should not be leaky, should not be having high leakage current. That kind of material we have to do that. So it's a kind of trade-off between the leakage current and thickness. So there should be enough thickness so that the current will not leak through the electrodes there. Okay, so that way you can decrease it to increase this. You can increase the area. And another thing is the epsilon, which is the dielectric constant of the material. You see, it's directly proportional. For example, various materials are there with different optical constant or dielectric constant, which is the epsilon. Okay. Okay. So this dielectric constant, this is a very important parameter. I'm going to tell you about the material in the last slide. Maybe at that time this will come into a picture. See, this material you need to choose with a high dielectric constant, so that its capacitance will be higher. Okay, so with that I will I will just go to the next slide. Yeah, otherwise I may miss a lot of things. This dielectric will also behave in a way that it will increase the capacitance of the capacitor. Capacitor. If you have any questions later, we can discuss that. Okay. Then charging and discharging of a capacitor. See, charging, as I told you, this is a capacitor. Okay, and it's connected through a resistance for a controlled supply, and this is a power supply, and that is a switch. So when you connect a switch, and this is a voltmeter which is connected across just to measure the voltage, nothing else. Okay, you apply proper voltage and there will be a charge buildup along this. Okay, so it will be charged, that's all. If you want, and then you open the gate, you open the switch, the charge will stay in it. Okay, so this is happening exactly like this. Now all theories are there in the book. I'm not going to talk about the theories here, but I'm just going to tell you. Okay, when you want to charge it, this is a function of time. You apply a constant voltage, which is the battery voltage here. It starts from here and it follows at particular time, it will saturate here, which follows this principle. Actually, the charging voltage, Vc, which is equal to Vs1 minus e to the power minus t by Rc. Rc is going to be called as a time constant. Okay, that is a factor for charging the the capacitor. So the charging curve goes like this. Okay, and charging will just follow this formula. The amount of charge which is built up is a product of this charge and applied voltage. So the charge capacity will keep on increasing actually. Okay, so that way you need to do that. And when you want to discharge it, as I say, you need to put a resistance here. It's not a resistance. Let's say this is a bulb. Actually, you can connect a bulb or some motor, anything, some load you need to give, so that this has to be opened. You don't need to switch it on because already charges are there here stored, and these charges are flowing through the bulb, and the bulb will glow, which means bulb glow consumes an electrical energy which discharges the capacitor. And the discharge curve, initially the Q naught is the initial amount of charge as a function of time when you use it for glowing a lamp, and this will discharge just like this, and this follows this. Discharge voltage is equal to Vs. Vs is a supply voltage which is connected, and e to the power minus t by Rc. Okay, so that is the one that follows the discharging. Okay, so this capacitor can be connected in different methods, and this one is the same that I have explained already there. This is a capacitor connected to a battery, which is exactly the charging methodology. Okay, when you want to charge the capacitor, you connect it to a battery. So that way of connecting, that's one way of connecting a capacitor to a battery to charge it. Okay, so all those things that I've discussed are just given here in this expression. Then capacitors connected in series. Okay, yes. See, capacitors connected in series. You know this actually. You might have studied in your undergraduate. When you connected two capacitors C1 and C2, and the voltage across them is V1 and V2, because they are serial, the total voltage should be equal to the supply voltage. Because that has to be conserved. You cannot have an extra voltage there. So the voltage drop across this and across this should be V1 plus V2 is equal to V. And you can write the capacitance. Capacitance is Q by V1, and you can write, Q by V1 plus V2. And if you substitute the capacitance there, this can be calculated the 1 by C total. We usually see effective capacitance, which is like this, 1 over C1 by 1 over C2, right? Usually 1 over C, that is an effective capacitance if they are connected in, series, which is like this, 1 by C1 plus 1 by C2. Usually we used to write C1, C2 divided by, C1 plus C2 divided by C1 times C2. That's called as an effective capacitance if they're connected in series. In a similar way, you can connect the capacitors in parallel. In that case, it's a voltage, and that's a voltage drop here and voltage drop here. So all these voltage should be the same actually across this C1 and C2. They are two different capacitors here. Okay. So when you use them, so the Q1 is the amount of charges built in the capacitor C1, and Q2 is the amount of charges which is built in C2, So capacitance of first capacitor is Q1 by V because the voltage is common here. It's also V, it's also here, V. So here capacitance of the second capacitor is Q2 by V. Total capacitor, if you want to add the total charges times, divided by V, Q by V actually. So the V, you can pull it common to this, V1, yeah, V and here V, so it's like Q1 by V, Q2 by V, and this like the sum of the capacitors. And this is very common circuits. We know that when capacitors are connected in series and capacitors are connected in parallel. Okay, so there are many types of capacitors available. Okay, one is a very common one is an electrostatic capacitor with a dry separator. There is a metal plate and there is a separator which is an oxide layer. It can be air or it can be any material like zirconium oxide, hafnium oxide, some kind of material. Okay, they are electrostatic. Nothing is moving here. Okay, just a dielectric, and charges are built up here and the other side, and it's just stored. Okay, they are electrostatic, correct? And this has a very low capacitance normally, like picofarads and even to microfarad. So and they have applications like in radio frequencies and filtering circuits. Okay, so first type is an electrostatic, and then another one is an electrolytic capacitor. So there people can use some kind of even the little wet separator. See, in this place they can have a paper which is mixed with or just to get wet. A wet paper can be built in between them. So that will be like an electrolytic, which is behaving like an electrolytic. There is no chemical reactions like in batteries, but only they will be assisting for the capacitance to be increased. So it gives higher capacitance than the electrostatic capacitor. And here the capacitors are in microfarads. Okay, here it's almost a picofarad, 2 microfarad, but here it is microfarad. Okay, these capacitors are deploy a moist separator and are used for filtering, buffering, and signal coupling. Okay, similar to a battery, electrostatic capacitor has a positive and negative. Sorry, here is an electrolytic capacitor. Okay, you need to observe the polarity because the electrolyte will have the polar side there. So you need to connect it with a proper polarity there. So the third type is the supercapacitor. And supercapacitor is a very particular type of capacitor here, which is very commonly people are studying them. And supercapacitor has 3 different, like the family. I mean, it's a family, and in that family it has 3 members. One is a double layer capacitor, another is pseudo capacitors. See, it can store the energy electrochemically with reversible Faraday charge transfer. Here, you can store energy using an electrochemical energy, and the reactions can also be reversed, which is like charging, discharging can be done. And double layer capacitor, which is a supercapacitor, in fact, they're also called as ultra capacitors. This double layer capacitor can also be called as double layer ultra capacitor. And what is happening here? You have one electrode, another electrode here. Okay, let's say you just charge it positively and you charge it negatively here. Okay, so usually you have an electrolyte here, but in addition to the electrolyte, you put a separate layer here. Okay, which is called as a separator. So because of this separator which is present here, near to the surface of the electrode, there exists an atomic layer thick charge will be formed here. So if you are applying a positive here, negative charges are assembled. So this local area will be acting like a plus negative at a small distance, here like a D. And this layer is called as a Helmholtz layer. Helmholtz layer, it is formed here, and also in this side is a plus width. So there will be a double layer formed, and this total capacitance will be like a sum of these 2 different capacitors now. It's like C1 connected, serially with the another C2. Okay, so there is a separator introduced in the electrolyte, and there will be Helmholtz region which is formed. Because of the smaller charge separation, it has an enormous capacitance. Similarly, you have another capacitance here. They'll be added together to give the total capacitance. Actually, when you take this supercapacitor, it is rated in farads. You see here, it is like picofarad. Pico is like, 10 to the power minus 12, right? And micro is 10 to the power minus, 6, correct? Pico is this, or Pico is on minus 9, no, I think minus 12. So you see, it is that big actually, the capacitance really so big, it is in farads actually. So they're usually used in heavy energy storage circuits, or wherever it requires, heavy discharging, supercapacitors are being used. These days, there are many high-end cars are coming with the supercapacitors to ignite or just accelerate many things. Electrical vehicles are coming up now. So they are planning, they are doing research, people, to replace the battery by using a supercapacitor, but still not, it's okay, because lithium ion battery is much better. Okay. In addition to that, you have a ceramic capacitors. See, these classifications are done based on the material that you are using here. So for example, you have an electrode here. If you're using ceramic here in between, then it is called as a ceramic capacitor. If you use film or some paper as a separator, then they are called as a film capacitor or a paper capacitor. Aluminum, tantalum, niobium, these are all electrolytic capacitors. And you can use this metal as anode or cathode. So these ones, you can use one of them as the anode and another as a cathode. So here, one of them will be metal, so accordingly it will be named. And if you're using polymer, they'll call as a polymer capacitors. Okay? Yeah. Advantages I told you, for example, the capacitor can discharge in a fraction of a second. For example, if 25 volt is just stored in the capacitor, that's a storage potential of the capacitor. If it needs to discharge it in a fraction of a second, all this 25 volt can be discharged just like that. Okay, it has a very large advantage, because in any circuit which requires a fast switching or discharge, it requires this capacitor. For example, capacitors are used for appliances which require high speed. For example, camera flash. You see, camera flash, that just very fast and consumes a lot of energy. For that, what we do usually, we have a capacitor fixed in it, and we charge that. Whenever you click it, it has to be charged again. I do not know how many of you have used the old camera with a large flash with the rechargeable batteries. People used to say that you need to wait a little bit of time to get the next flash. If your battery is weak, when you put a new battery, the flashes will be very fast. You can just keep on clicking every moment. But after some time, you can click, but the flash will not come. Because why? The capacitor used to initiate is not charged enough. That's why they give enough time for the capacitor to be charged. Then you click, then it will flashes. Otherwise, normally batteries won't just able to meet out its a fast discharge of the flashes here. And similarly, laser, when you want to use the pulse laser, capacitors are much important for that. Okay. And similarly, used to remove the ripples by removing the peaks and filling the valleys. For example, let's say you have an alternating current here, and you want to filter it. Alternating has a positive and negative, correct? So you have this. And if you want to use that in a rectifier, or just if you want to convert an AC, a DC, you have a positive, only, you just filter it and only you have a positive one. But this is not the real filtering or DC current, DC means it has to be perfectly straight, right? So whenever it has the lower end, this, the gap, they connected this, they connected capacitor here. So when the voltage goes below and this capacitor gives the current, supplies the voltage. So this will be like slightly lowering, that's all, slightly lowering. So this ripples will be removed from this, and that's done by the capacitors, okay? And that, actually capacitors allows AC voltage to pass through and blocks DC voltage, and therefore it can be used in rectification, okay? That. Rectifiers, okay? Yeah. Now, let me move on to the MOS structures. That is the main thing. As I said, the acronym stands for metal oxide semiconductor. Metal oxide semiconductor, okay? So, all the MOS capacitors, I can just go to the image and show you. That's better actually. It is metal oxide semiconductor. Sometimes it says MIM. People used to say metal insulator metal. Okay, this we are not going to see. I might use it for some examples, but it is the same almost. So we see MOS here. See, metal is given as one of the contacts on the top, and that is called as a gate metal electrode or gate electrode. That is a contact which is given at the top, actually. Okay, and oxide are an insulator. In a general way, it is an insulator, but we use oxides all the time. That's what's called as an oxide layer. Here it is an oxide layer. Okay, that is being used here. And semiconductor is in substrate, which is mostly either P-type silicon or an N-type silicon. What we discuss is all based on a P-type silicon. Okay, P silicon otherwise. You know, it's heavily doped with holes actually. So the majority carriers here is a P. So that's what we're going to see. It can be an N-type also, doesn't matter. So this is the MOS structure. Okay, so it's like metal, oxide, and semiconductor. So this is a schematic, but what you see is the right side is a real image of the metal oxide semiconductor. You look at this. This is the, it is the STEM image. Let's say it's a TM image. Okay, you know, I'm good in doing TM, so I will show a lot of TM images actually. Okay, this is a TM image which was, this transistor was cut through, and I look this way. So I see the metal layer, insulator layer, and semiconductor layer. You understand that I cut this across. It's a cross section. I made a slot, and I'm looking through this, and what I see is that. Okay, I see an aluminum layer, which is the top layer here, from the top, which is the metal layer. Let's say this is a metal layer. Okay, and here the silicon dioxide, which is a very popular oxide, even today, that is being used in many of the, you know, electronic components. So that is an oxide layer or an insulator layer, let's say this. And at the bottom, there is a silicon. Okay, so this is a real image or real device. Look at that, there is an interface here, and there is an interface. There are two interfaces, one between semiconductor and oxide, and another is oxide and metal interface. Okay, this is called as an interface. Interface in the sense that, you know, it is a junction between two different materials or two different states, let's say this. So this is exactly one interface, and this is another interface. So this interface, we are going to see a lot in our discussion. I hope that when I talk about interface, you can recollect what I mean by an interface here. Silicon and silicon dioxide, there is an interface between them. Silicon dioxide and metal, and there is an interface between them. Okay, because there are a lot of charges are going to be here in this interface, we will see them. Okay, yeah. See, I'm just listing some of the commonly used oxides in the place of oxide layer, what we're using. And gate metal electrodes, it's not just aluminum, copper. We use gold, we use platinum, we use silver, many of the conducting things. And these are the mostly used metals, actually, as a, you know, metal electrode. And substrate is normally the semiconductor here. Okay, but in many of the cases, the gate metal electrode will also be used by heavily doped polysilicon. Heavily doped polysilicon, polycrystalline silicon. You know, in this place, they quote polycrystalline silicon also, which is heavily doped with electrons, so n-doped actually. So electrons will also be, that behaves like exactly like a metal. Okay, but now I don't know, people that are using polysilicon, mostly they use metals only. Okay, that is a structure. And this is the band diagram of the, you know, you don't need to worry too much about this, but still you understand that this is the metal side. This is a metal side, this is an oxide side, this is a P-type semiconductor. Okay, so metal has this Fermi level here, and its work function is given by this. This is the work function, and this is Q. If you multiply this work function potential, voltage that you need to apply to eject an electron from the Fermi level to vacuum level. If you multiply to the charge, it's like UV, it's an energy. Okay, it's an energy level. It is an energy scale. Similarly, this is an oxide layer, and it's, you know, it has a large band gap, so it's not given here. And if you look at the, actually, it has a band up to this, really high energy, I mean, high band gap there. When you come to the, semiconductor, it has a valence band, and it is the Fermi level here, it is an intrinsic band, actually it's a conduction band. And, the, the energy between them is just marked by different letters. Just, it's half of the band gap, actually that's why Eg divided by 2, which is given here. And it is another, it's the energy difference between the intrinsic state and the Fermi level. And this is the Fermi level of the semiconductor's total energy level difference. It is the work function of the semiconductor. So in any energy band diagram, of course, I'm taking p-type mass at V is equal to 0. You are not applying any voltage. When you make them a contact, the Fermi levels should lie in the same level, actually. And this is also going to be called as a flat band condition. Flat band, all the bands are flat, okay, looks exactly flat. And also the Fermi levels are the same. It's an undisturbed condition here, okay. So in this case, the total work function of this, the total work function of this should be equal to 0. That is what is being explained here. Okay, this is the MS, it's metal semiconductor work function totally. That should be the difference between the metal and the semiconductor work function. This is interpreted in terms of these, all these three. If you carefully look at that, you can see that, okay? And which is supposed to be 0 here, and that's what is equated, which is the undisturbed condition. You're not applying any external voltage to that. When you apply voltage, and these bands will not stay straight. It can either bend this way, it's bending down, or it can bending this way, it's bending up, depending on what voltage you're applying to this metal, gate or metal. That's what we're going to study that, okay? Then it will be band bending. Here it is a flat bands, actually, okay? Yeah. See, for an ideal mass, ideal mass means you're not applying anything. See, ideal mass is a structure for which it is assumed that there is no work function difference between the metal gate and semiconductor. If you take, this is a metal gate and this is a semiconductor, there should not be any difference between the metal work functions of these two. So that's if you minus one from the other, it should goes to 0. Okay. And there is no charge at the semiconductor oxide interface. Okay. Which means this is a semiconductor and this is an oxide. And this is an interface throughout, this throughout. There should not be any charges aggregated or accumulated in the interface, okay? And also, there should not be any charge in the oxide. This is an oxide, you should not have these separated charges here and there. That is not supposed to be there, okay? So those kind of things, it's an ideal mass, and this will happen when you don't apply any voltage, or sometimes you might have to apply a little voltage so that the energy bands in the mass structure are horizontal, are flat, okay? So, this will be happening only at the 0 voltage. There, the bands are flat here, like this one, the exact case as I said, okay? So, yeah, so any departure from the ideal condition will change the potential distribution across the structure. If you apply any voltage or if you do anything, there will be a charge redistribution between the oxide layer and a semiconductor layer, then the charge will accumulate, then the whole dynamics will change, we have to characterize them, okay? Now, see, this is a very important picture actually for understanding the mass structure. I can go up to 530, correct, Prakash?
630.
Sorry, 630, right. Now already we crossed, yeah, 630, right? Yes.
That also you can do.
What?
No, you may take little more time also.
Okay, okay.
No compulsion.
Yeah, okay, right. Yes. See, now the point is that, see, this has to be connected actually. Okay, most of the time this will be grounded. I'm writing it's all the time, it is the silicon semiconductor, P silicon, and it is an oxide layer, and it is the metal contact. So you have your M, you have your O and S. So hereafter everything is MOS, nothing else, okay? Right. So, and this is the band diagram here. See that? So when you want to apply a voltage to the gate, gate voltage is the voltage that you need to apply to control the flow dynamics of the current into the capacitor. Okay, so gate is actually like a gate. If you want to stop the flow, you can increase the voltage or decrease the voltage, or if you want to make the flow to happen, you can do something. Okay, so by applying the voltage, what is the change happening here in the capacitance? We are going to see that there are three cases. We apply a voltage, for example, and the voltage is going to be separated into three different cases. One is V is less than 0, which is V is negative here. So we are going to apply a negative voltage to the gate. All are equal, but given in a different forms actually. You should understand that. So I'm applying a negative voltage, which means that I'm putting a lot of electrons inside. So the Fermi level of the metal is gone up actually. So when the Fermi level is gone up, okay, all these bands are trying to match the Fermi level. So the bands which were flat at that time, because of the negative voltage that you apply, negative voltage means you're putting negative charges. So in the metal, the charges are negative here. That's a QM, which is separated, which is deposited here, or which is stored in that. So the negative charges will be accumulated. According to that, it cannot be a completely one side charge. Equivalently, that should be another charge should be developed or generated. So first of all, the Fermi level will be increasing here. So these bends, these bands will start to bend here. You see, previously this band was supposed to be here, this EI. Now you see the Fermi level of this semiconductor side remains the same, but because it bends this, now the difference from here is increased to this. That is what is given by this. You see, the bands near semiconductor surface bent upward because you put more charges and you moved the Fermi level of the metal up actually. So the bending will be happening there. So because the negative charges are built up on this side, according to that, this is a P side of P-type silicon. So these positive charges will just come and accumulate here near the semiconductor interface. Okay, and this concentration or the okay, which makes, because of the band bending, it causes increase in the energy difference EI minus EF, and the difference between this will just bend it, and carrier density in the semiconductor depends exponentially on the energy difference based on this. This is a carrier density in the P-side silicon, which is depending on this difference. When this is increasing and your carrier concentration increases, which means that a lot of holes, actually here holes because positive charges are the main carriers in the P-type silicon, and they come and accumulate at the interface of this. Okay, so that is why you get equivalently the charges accumulated in the oxide interface here. Oxide here, this is a semiconductor, and Q is is just it is exactly here, this place. Okay, it's accumulated. See, the same thing is shown here. When you put a negative charge, you have negative charge on the top, right? So naturally, if this is a negative charge, it is being negative charge actually. So positive charges are being, negative charges are being pulled here. Equivalently, when you have a negative charge, okay, it's a thin one. You see, accordingly, you have a negative charge here also. It will be developed. Sorry, you have a negative charge. You put that here. When you put a negative charges, you have a positive charges developed. Okay, you can put that here. Positive here, then naturally it will be negative on the side. It's kind of polarization. To compensate this, you have a negative charges accumulated here. Okay, so what you do, you are applying a negative voltage to the gate. You accumulate charges in the interface of the semiconductor side actually. Okay, it is the oxide semiconductor interface. In this interface you accumulate, and this kind of behavior is called as an accumulation case or accumulation side, where the capacitor accumulates charges near the semiconductor interface. Okay, when you apply negative voltage, there is an accumulation taking place. So naturally, okay, that is the first case when my V is negative. The second case, my V can be positive. It's not so positive, but it's a little bit of positive here, So when you put positive here, naturally, when you put positive in the plate here, so the first side, the side of the dielectric will become negative here. This is silicon dioxide. This is silicon. Okay. Accordingly, you have a positive charge is developed here. Once positive charge is developed here, and here the majority carriers are positive charged holes. So this positive charge, what it will do, it will pushes them away. It will say, come on, you are a positive, I'm also positive, get lost. So there will be a layer formed which is called as a depletion layer, which means the region which is depleted of charges, depletion layer. Okay. So what will happen? You put a positive charge. So you are pushing down the Fermi gap, Fermi level of this metal down. So accordingly, and this will be going down here. So naturally the difference will be is getting lower. So accordingly the charge concentration will get lower in this area. At one point it will be pushed away. Okay. So this is the depletion region which is formed here. And this W is the width of the depletion region here, which is equal to this. Okay. So whatever be the amount of charges here, positive charge you put equivalently, that will be a depletion, that quantity is a depletion layer, and that much of the thickness layer will be formed here. Okay. So the space charge per unit area gives in the semiconductors given by the charge within the depletion region. But there is no charge actually, but the depletion region is equivalent to that. And this is the depletion layer which is created here. So when you apply a little positive charge, there will be depletion layer created. Now you see that this area will be behaving like a capacitor with the CO, which you call as an oxide layer capacitance. Additionally, you will develop here one negative and another positive here. So this will be like another capacitor, which we will be calling it as a CS or C. Some people use C deep. I mean capacitance, C depletion capacitance. Okay. So in this case, when you are depleting your mass capacitor, this will be looking like a series combination of two capacitors here. Okay. One is C naught, another is CS. That is what is exactly happening here. Okay. Now, another term, another biasing here, the V is very much larger than plus. I mean, 0. There it was just a plus, but here I'm just applying very high voltage. Okay, compared to the initial voltage there. So when I apply very high voltage, see my Fermi level of the, this metal will be pushed downwards so much. Accordingly, the band bending will be lower. You know, exactly it intersects there. Okay, so there will be a small layer which is formed here in between them. You know what is this layer? And this layer is called as an inversion layer, inversion region. Actually, what happens, let's talk about that first. See, because of the heavy voltage, naturally, when you take in a very simple meaning, see, here you're applying heavy voltage. Accordingly, this depletion layer, there are more and more of positive charge you're putting here. So naturally, this thickness will be increasing, and this is what exactly is happening here. Okay, this is exactly is happening here. This WM, that's the width of the depletion layer, is being extended here, which is taking place in the semiconductor side. Okay, and you see that the depletion layer is really huge actually. Okay, and this D is this D. The thickness is being increased, and again it is capacitance is like CS1 maybe we say that because it's like with a huge depletion layer. See, because of the huge voltage, there would be thermal electrons are usually formed here, and out of these thermal electrons, thermal electron will not forming just out of nothing. In the semiconductor, you have the valence band here. So because of the thermal instability raised from the high voltage that you're applying, here you have the holes here and you have electrons. And these electrons will just make a small layer close to the semiconductor interface, and these holes will be pushed towards this. Okay, here you have a positive side, and your electric field is very strong because of the high voltage that you are applying. And once this this electron hole pairs are formed, these electrons will go and just go closely to the semiconductor, makes a small layer, and which is called as an inversion layer. Okay, and it makes furthermore holes that will be pushed down further, and more charges also will be there. Okay, so when you apply more and more, see this layer is supposed to be positive, now it's inverted here negative. So that's why it's called as an inversion layer. Okay, instead of the, here it is supposed to have the positive charges because the p-type charges, but you developed a negative charge in between the oxide and the semiconductor, which means you inverted the nature of the charge which is present in the semiconductor. So that is called as the inversion. Okay, so there are three cases you can apply. One is V is a lower voltage, negative, a positive, and more positive. When it's negative, that condition, okay, let me explain here, summarize here. You see, this is a curve that you are going to see that. This is the capacitance versus voltage curve. Voltage means that's a gate voltage that you're applying. Okay, we are applying a gate voltage and we are measuring the capacitance. Okay, the first case is here. Let's compare this graph with this. This is a very special case. I'll talk about that. See, so in this case, I know that, here you form a capacitance. So only Cox or CO, let's say this. Only this capacitance is just because of the CO. So here in accumulation region, where I'm applying the negative voltage, you see this is a negative voltage axis. Whenever I'm applying a negative voltage, the oxide layer is in accumulation side. So the oxide capacitance is exactly like a C oxide. Okay. C oxide in the sense that, it's, if you know the dielectric constant of C oxide divided by the thickness of this layer, if you know this, let's say thickness is like Tx, that is the capacitance of CO. Okay. So that is one layer. Now you're switching to the positive side here. I should have extended a little bit further here. Okay. So when you go from the small positive, and here is the layer, and now you have the capacitance, two capacitance. That's the condition here, it's given here. Okay. C0 connected with series, series with CS. CS is this capacitance. Okay. But you see, when you have two capacitors connected in series, the total capacitance is like 1 by C0 plus 1 by CS. And CS is so small here. So the CS will dominate. And when you increase the voltage from 0 to here, and this layer is increasing, when the thickness of the layer increases, capacitance will decrease, so that effective capacitance will decrease. Okay, that is why when you are entering into the depletion layer, so the capacitance is going to decrease here. Okay, but this is happening up to certain point. Okay, after when you are applying a really high voltage, there is an inversion occurs. Therefore, see, this voltage is like really a small voltage. It will become really negligible, and the oxide layer capacitance alone will exist here. So in this case, this is called as an inversion side, and here what you see is exactly the oxide capacitance alone. Okay, so it will come back to the oxide capacitance, and usually people call this as a low frequency capacitance. Okay, this case occurs only when you apply the voltage with a low frequency of the order of 10 hertz, maybe 50 hertz, 100 hertz, not more than that. When you apply a really high voltage, this region is generated by the formation of the electron hole pair. You have a electron there and you have a hole there, and this electron hole pair has to be accumulated by a heavy voltage. So this needs certain time. Okay, this occurs only when you have a low frequency signal, which means you change the voltage very slow. The time constant or time of varying this voltage in a very slow manner, you get this kind of curve. If you don't do that, if you apply it very fast, you see, and this is not happening. The inversion is not happening exactly like this. So still you have a depletion layer, but this inversion layer will not be strong, and that's why this is the capacitance will not increase. The capacitance will just stay as low like this, and this is called as high frequency side, high frequency capacitance. Otherwise, they say it's a weak inversion region, region. And this one, if it happens like this, and that is a strong inversion region or low frequency inversion region. Okay, so if you fabricate any kind of this kind of mass capacitors, and if you measure the CV, it comes like this or it comes like this, or the depth more, whatever. From the behavior of the CV characteristics, you are able to understand and what is happening in the mass capacitor. Okay, how much of the depletion and many more things can be calculated. We will see one by one here. Okay, yeah. See, these are the three active regions basically in accumulation. The total capacitance is exactly equal to the oxide capacitance. The depletion, if you take the ratio, I mean, okay, it's C naught times this. Vg is gate voltage and is an oxide potential, which is potential developed across the oxide layer. That's a V0. Similarly, the inversion region is a C minimum, I say. It's not the C maximum, okay? That is the high frequency signal, C minimum. And C naught, if you know this, it's a threshold frequency, I mean, threshold voltage to the V naught. So I forgot to tell you what is the threshold voltage. You see, the voltage at which strong inversion takes place. See, I have marked here already Vt. Now you are applying, you are applying continuously the negative voltage and zero voltage, then positive and high positive, right? At some point, it is accumulating at one point, and then it will enter into the depletion region. From the depletion region, it will enter into the inversion region. Where it enters the strong inversion region, that voltage is called as a threshold voltage. Okay, so from that, the capacitor will work in an inversion region, correct? Yeah. So those parameters are given here. See, so another important thing is that you should understand what types of charges which are normally packed in the oxide metal. Let me go a little bit faster. See, this is a metal, this is silicon dioxide, this is silicon. There are fixed charges which is fixed actually, which is a totally a constant one, which are naturally available there. And these fixed charges are available about 100 angstrom unit. They're fixed about 30 angstrom unit from this interface. Okay, and another set of charges which are present in the exactly right at the interface. Here, the crossed ones, they are called as the interfaced trapped charges. And in between them, within the bulk, there are different charges. They are of bulk type actually. Ionic charges can be there, or oxide trap charges are there. These are various types of charges which are available in the metal oxide capacitors. So what are the observable from the CV measurements? Let's say that you are measuring the CV measurement. What you can measure that? You can measure the oxide thickness. You can measure the flat band voltage. This is a voltage at which there is no net charge at the semiconductor oxide interface, and also in the oxide, that is the case. And all bands are flat. That's what's called as a flat band voltage. And we call that as a flat band capacitance. The capacitance related to the flat band voltage, for example, you measure the CV like this, right? CV, let's say this is your flat band voltage VFB, and the capacitance corresponding to that is CFB. Okay, this flat band capacitance. And you can measure the threshold voltage and what are the types of charges which are present in mass capacitor. Okay, yeah. See, here after all the, most of them are, you know the CV curve, which means that you know the CV, you know the capacitance actually as a function of voltage. Okay, that's what the meaning. Excuse me. You see, you know the capacitance and voltages. From that, you're going to calculate that. Okay. So if you want to calculate the oxide thickness, you should know the area of the plate or the area of the electrode that you are using, and the dielectric constant of the material, and the capacitance of the oxide layer. Okay. You can calculate it from the accumulation capacitance. This is also going to be compared with the geometric capacitance. Why it's going to be compared with the geometric capacitance? I told you, oxide is the layer which is here. This is your metal, and this is your semiconductor. So the length and breadth of this one. You can calculate the geometric capacitance, which is like epsilon naught A by D. That is geometric capacitance, we normally say that. And that should be exactly equal to the oxide layer. But in this place, you should not use this epsilon naught. You have to use epsilon R and epsilon naught. By using the dimensions, both of them should be the same. Okay, that you have to calculate. If there is a 5% difference between the geometric capacitance and the oxide thickness that you are calculating, then you have to redo the measurement. There should not be much change. Okay, yeah. Then this flat band voltage, if you want to calculate, you can calculate by using this formula, by knowing different types of charges and the metal semiconductor work function difference. Okay, and they are defined here. So for a particular system, it is different. You can know it, and by knowing all these parameters, you can calculate the flat band voltage. And once you know the flat band voltage, you can straight away calculate the flat band capacitance from the graph or by using this expression. And here one more term is there, which is called the d by length. All the terms are just listed here. By using this, you can calculate flat band capacitance. And if you want, you can calculate the threshold voltage also by using this formula. And effective and total bulk oxide charges can also be calculated once you know this flat band, and also this the work function of the metal semiconductor. Then you can calculate the capacitance of the oxide, this. Then you can calculate the Q effective, which includes all the charges which are present in the oxide layer. Okay, yeah. Again, it is few more determination of minimum depletion layer capacitance and dopant concentration in the oxide layer, flat band capacitance by using another formula. Those things can also be calculated. Okay, once you do the CV measurement, many of the capacitance, capacitor parameters can be calculated either by using a formula or by using your CV curves. Okay, yeah. Now, here I'm not going to spend much time here, but another important parameter for the mass capacitor is the leakage current. Okay, you have your dielectric, and you have your two layers. As I told in the very beginning, this is, let's say, metal, this is semiconductor, this is oxide. Though the charges are expected to be here positive and here it is to be negative, this is supposed to store. But that in the real case, it's not happening exactly. Why? Because the whole world is going for miniaturization. If we keep the thickness of the layer 2 millimeter, 2 centimeter, for example, or 2 millimeter, it's quite thick actually. Then these charges will not leak through this. Okay, then there is no current, which is called as a leakage current. But now the technology is taking us to miniaturize everything. So they're going for a real thin film, about 0.5 nanometer or 1 nanometer, 1.5 nanometer. Okay, they're all going sub-nanometer thick films here in between the electrodes of this mass capacitor. Mass capacitor includes all this mass family. Okay, CMOS, PMOS, or MOSFET, whatever be that. Even quantum field effect transistors are there. So when you reduce the thickness of few tens of nanometer, then the material is susceptible to leak some charges through that. It won't behave like a perfect capacitor that you used to see, like a cylindrical capacitor with 2 leads here. This will be in the, this won't leak. Once you charge it, won't leak normally, because the thickness of the layer is quite large in this kind of regular capacitors. But the mass capacitors, the thickness of the film is about a few nanometers, a few tens of nanometers. So the leakage current is a big issue, and we have to find a material with a low leakage current. So understanding the leakage current through the dielectric layer is very important. Okay. Now here I'm giving the results of our work which was published recently. So I'm giving that just to give you what are the types of leakage currents are there. That's all. Okay, not much actually. So you see, our film was a semiconductor which is silicon. Underneath we have to coat something to give a contact actually, which will be earthed actually, but still through metal we have to give that. So this is silicon, which is a p-type silicon again, and the top electrode is silver electrode. This is silver. Okay, Ag silver. Anita Raju is joining now. Okay. And in between them, you see the dielectric material. Watch what we have used is Mg doped, actually. That's what is written, Mg doped zirconium oxide. Zirconium oxide is a material which has high dielectric constant epsilon. You might remember still capacitance is equal to epsilon naught A by D. I told you epsilon naught maybe epsilon, let's say this. Epsilon is the dielectric constant of the material here. So I'm looking for a material with a high dielectric constant. One such material is zirconium oxide, but we wanted to use the zirconium oxide in a particular phase, crystalline phase. So we dope it and made that into a cubic or tetragonal phase, and we fabricated this MOS capacitor to measure the current density versus voltage. We applied a voltage here, negative voltage, which we were in an accumulation region, and we have studied the current density, which means the leakage current. This is the leakage current. Okay. Okay, this is in a point minus, that's quite high leakage here, but still we studied the mechanism. This is the leakage current behavior in the capacitor. And this leakage current, if you want to understand, this leakage current follows many principles and laws which were formulated by great scientists actually. Okay, to understand this leakage current or current conduction mechanism in mass capacitors, we used various models and we studied this IV by using them. Okay, so in the slides I will be saying that. I don't know you would be able to understand that. It's just for your information. Let's see that. Okay, one type of emission will be Schottky emission. There will be a Schottky barrier. By considering a Schottky barrier, using this formula, we have plotted in a particular way, and wherever the linear region is present, then that region follows the Schottky emission mechanism for current conduction in that capacitor. Okay, that is what it is done here. Okay, yeah. Yes, there are many types actually. So this is one type, and we have used it and we plotted that same curve, what I have shown here, the same curve. This curve is plotted in different styles. We're using different mechanisms, and we found some flat regions. And similarly, another mechanism which is here, Pull-Frankel plots actually. Some other voltage region, here it follows the flat, and it says that, when you apply a lot of, huge range of voltage, in particular range, it follows the Pull-Frankel plot. That mechanism is given by this, and it's space charge limited current conduction, and that is this, I believe. Yeah, this is space charge phenomena, and we use the formula, and we found a very linear side here. Okay, and similarly, we have this Fowler-Narham tunneling, and this is the Fowler-Narham tunneling mechanism. I think we plotted it, and there is another region which is exactly flat, and just to marked it, and that is the region which follows the Fowler-Narham plotting, mechanism, and there is a trapezoid tunneling mechanism, and we used this formula and we plotted that graph here, and we have seen the particular region. So there are very different mechanisms are available. In some material, some mechanism will be followed, and some other mechanism will be followed. And this is a post-analysis of your IV characteristics or current density characteristics in mass capacitors, and we have done that. Okay, yeah. I have less time, and let me go a little faster. See, that's all about the mass capacitors' electrical behavior. Okay, we studied about capacitors, and we studied about mass capacitors, and now we are going to see fabrication of the mass capacitors. Fabrication, I told you, you need to have a substrate, which is the silicon semiconductor space, which is a substrate, and on which you need to coat a oxide. Okay, on that you need to coat a metal layer. So 2 layers at least have to be coated on the silicon substrate. So you need to have the thin film coating technology to fabricate them. Okay, so I'm going to list them, some of the technologies and some of these methodologies. If you have any questions, we can discuss that. Okay, these are the thin films. Okay, so we are supposed to coat the thin films here. Thin film is a layer of material. Our thickness varies from a few nanometer to a few micrometer coated on a substrate. So you can coat it on any substrate. Okay. So this is the same image that I have given. So here exactly it was a thin film coated. See, this is the silicon dioxide substrate was taken, and that silicon dioxide was coated or aluminum coating was done. Okay. This is scale bar. By knowing the scale bar, you can measure the thickness, which is about approximately 50 nanometer maybe. And this can be anything, doesn't matter. Okay. That is the top electrode. So thin film deposition, basically, what you do, you have your source material. For example, if you want to coat zirconium oxide, you will be having a zirconium oxide target here. Or if you want to coat Ag, which is an electrode, you have Ag here, and evaporate them, and which means that you will convert that into a vapor phase, and the vapor will come and deposit on your substrate, which can be silicon here. That coat, there are many deposition techniques are available. Mainly they are physical methods and chemical methods. Under physical methods, you have thermal evaporation, electron beam evaporation, molecular beam epitaxy, sputtering, or deposition. Okay, they have their own methodology. In chemical methods, you have a chemical solution deposition or chemical bath deposition, LB technique, Langmuir-Blodgett technique, or CVD, chemical vapor deposition, or plasma enhanced CVD, and many more techniques are there. I'm listing a few here. Okay, so the same thing here. So this is one of the techniques that we used in our PhD. I think still it is alive in nuclear physics department. That's why purposely I'm giving this technique. This is a physical vapor deposition technique. We call this as the inert gas condensation method. Okay, we have a chamber like this, which is steel chamber. Okay, and steel chamber which was evacuated to a high vacuum by using various pumps. And there is a source which is a cup kind of stuff, like a boat, we say metal boats, like a molybdenum boat or tungsten boat, high melting point boats, we have it here. And it was electrically connected to a power supply. Okay. And we keep our silver. For example, if you want to coat silver, we keep our silver here. And we supply an inert gas. Most of the times we used argon gas here. So once argon gas is there, we evaporate it by using a power supply. See, and this particular method was used by us for making powders by having a substrate holder here. Here is a substrate holder. We send a coolant, which is the liquid nitrogen. So, when we heat it, you see here it's a high temperature. And when you cool it here, it's a low temperature. Because of the thermal gradients, this will go and just deposit. And while going, because of the inert gas, they will form a particulate and deposit on that. Okay. If you want a powder form, you can just scratch it later. If you want a silicon, you can put a silicon here, and this vapor and goes and deposit in silicon on the silicon wafer. Then thin film of the material that you keep will be formed. Okay. And this method is called as an inert gas condensation technique. And why I put purposely, because this will give a space to Dr. Prakash to take you possibly to, maybe not to the physically, but at least to by camera wise to the nuclear physics department, can show this, and maybe inner side also, or he might be having movies already taken from there. He also worked in it for his PhD. So you can visit that. Okay. That's one of the techniques that we use it. I'm not going into the details of them actually. Okay. So another technique is a thermal evaporation, which is also similar to the inert gas condensation, but here we don't use an inert gas condensation. Okay. Thermal evaporate it. Like the way that you cook your food at home, there is a metal boat, which is a high temperature boat. They're electrically heated. There are two things, you supply voltage, and this boat will be electrically heated, and you put the material on that you want to evaporate that. So this material will be heated by Joule heating, and it will evaporate. So, you can use the low vapor pressure materials, high vapor pressure materials, and this evaporated material go and deposit on this. This will also be done under completely vacuum, because you don't want the samples to be contaminated. Okay. You just heat that thermally. This is all the same thing. Yeah. And another case is an electron beam evaporator. Okay. So the principle is the same. When you take a crucible, you put your material here, and you send an electron beam appropriately by having an electron gun. This high energetic electron beam hits this and locally heat it and evaporate the material. Once it's evaporated, it is the same process. All the chamber is in vacuum. You can put here a wafer, in the sense it's a substrate, and this vapor goes and deposits on this substrate. Then you can take it out. Okay, that's an electron beam evaporator. And another method is called as sputtering, which is a commonly used technique in our recent technology. Even in these days, while fabricating all your circuits, this VLSI technology commonly they use as this physical vapor deposition technique. They use it very commonly in silicon technology. All your mobiles, your computers, all your electronic gadgets, one of the components at least are fabricated by using the sputtering technique. Okay, you can coat literally by using the sputtering metals, ceramics, and organic materials. See, what you do that here, let me, you have a high energetic argon ion, which comes here. Okay, let me say here, this is the target. Target means the material that you want to evaporate. Okay, right. And you allow argon here, and electrically you ionize them, then you get an argon plasma there. Okay, and this plasma will be accelerated towards this negatively charged cathode, and where this target is fixed. So this argon is positively charged one. These ions will be accelerated towards the target with a high energy, and then the argon ion hits them and physically removes them. It is like you throw a ball on something, the ball will go and physically remove the material atom by atom here. Okay, so the substrate atoms will get out of this and they go and deposit on a substrate. This is called as a sputtering technique. Okay, it can be RF or DC, but that is used to coat the materials. Another is pulsed laser deposition. Again, you have a chamber, this metal chamber, completely evacuated, and you have the target material, and you put your substrate either here or here. Okay, and you send a high energy laser beam. It physically heat it up, and it ablates them and removes the material, and the removed material deposited on the substrate. Okay, it is by laser ablation actually. Laser will really take the material out. This is really a complicated technique. People do not understand exactly what is happening. So advantages and disadvantages are listed here. One of the disadvantages here is this: any material can be evaporated. Okay, any material can be evaporated without loss of the other material. Literally, stoichiometric films can be deposited. Okay, yeah. So the next topic is understanding the layers in the MOS capacitors. I'll quickly go through that, which means, you grow a layer and you want to understand what the layers are. Okay, I used the TEM and EDS here extensively. TEM is transmission electron microscopy. EDS is, energy dispersive spectroscopy. Okay, you might know this actually. Maybe EDS you may not know. I am writing, which is energy dispersive spectroscopy. Dispersive spectroscopy. Okay, by understanding the energy of the X-rays which is coming out, you can tell what the elements are present there. Okay, so I'm going to basically use the transmission electron microscopy and this EDS to understand the layer. Okay, so this you know that I don't need to tell you exactly. This I have shown you, right? I want to characterize this layer. I want to study this layer. Okay, what I have done here, I have acquired a EDS, which is an energy distribution along this line. When I click here, you see this. The image is inverted here. See, this is my silicon, this is silicon dioxide, this is my metal aluminum. Okay, so I make an elemental map across this layer. When it goes here, I plot. See, this is a silicon distribution. See, and this layer is a silicon layer, 100% silicon. So when silicon is there, I get a really high intensity, and from silicon, this line enters into the silicon dioxide. It is not purely silicon, silicon and silicon dioxide mixed. So it is going down, but still silicon is there. Now this is an intensity here. But now the silicon enters into aluminum here, and this is completely aluminum. I'm hiding it. There's somewhere aluminum, it will up here. Now I will show you. See, this is an aluminum distribution. When silicon goes down, aluminum picks up. This is an aluminum distribution in this layer. Let me go back here. Okay. After aluminum is crushed, this is a platinum layer, and you can look at that. When aluminum is finished, platinum signal picks up. And this is exactly the map of each layer what is present here. Okay. And you see, look only this red color one. This is for, sorry, this is for my oxide layer, silicon dioxide. So if I want to measure the thickness of this layer, I can use this. I can use this spectrum. How? Let me say it in the next slide. See, this is the spectrum, which is plotted, which is an oxygen distribution along this. Oxygen is distributed only along the silicon dioxide layer. So that is this distribution. So I'm taking the oxygen EDS spectrum and fitting this with either Gaussian or, Gaussian mostly, or the Laurentian. I take the FWHM, which is a full width of maximum. That gives me the layer thickness is about 92 centimeter. Okay. That's how I do that. I understand how much is the thickness of my layer. It is 92 nanometer. So that's what one of the analysis. Okay. This is, again, you look at that very carefully. This is another MOS capacitor. Here the silicon. This is dielectric, which is hafnium based. And this is the platinum metal, I think. Yeah. See, look at this is my oxide layer. This is a TEM image, transmission electron microscope image. You look at the thickness of the film, which is 4.3 nanometer. Okay. This film was as deposited, heated at 750 degrees centigrade and heated at 1000 degrees centigrade. When I heat this, these are already a bilayer. It's not a single layer. Okay. We understand that there are two layers, and one of the layers, when you heat this at 1000 degrees centigrade, is converted into a kind of lines. And this means that this is becoming crystal or crystalline arrangement actually. Okay. All these layers are amorphous in the beginning. When you heat that, this becomes crystalline. You are understanding the behavior of the layer for different treatments by using this microscopy. Okay. Yeah. This is another capacitor, which I call it as an MIM capacitor, because, on silicon, I put another metal layer here. Metal, all these are oxide and metal layer. The only thing you should understand that there is a tantalum and rest of them hafnium, silicon, hafnium, titanium, all oxides, multi-layers. And the top is a platinum. It's a kind of MIS, how beautifully we have done it. You see, this is a coating, you don't look at that. This is a coating we have done, and this is a TM image. And every layer here, by seeing the contrast, if you look at that carefully, we have demarcated the layer boundary. This is tantalum pentoxide, this is hafnium nitride, the silicon oxide, and various layers have been demarcated by using the transmission electron microscopy. Okay, that's what done here. It's not important for you. Yeah. Yeah. Okay. Let me see this. Let me show this. See, this is the same layer, which is the 5-layer, 6-layer coated one. See, this is the TM image. And I acquired, this is my oxide layer, totally this oxide layer. I wanted to see all the oxide layers. Okay. See, I acquired EDS spectrum from this point. You see, when I'm acquiring from this point, every peak can be assigned to a particular element that is present. For example, I see tantalum here, tantalum a lot. So I'm saying this spectra from this is containing tantalum more. So tantalum is there and tantalum pentoxide is distributing for a while. Then I acquire from here, that spectra is here, the second here. See, I get titanium, hafnium also a little bit in addition to tantalum. So this layer, approximately this one, is a mix of titanium and tantalum. And I go to the third region, which is mostly titanium, and there is no tantalum. Already, so tantalum is not there in the layer. And a little bit of hafnium and a little bit of platinum, might be platinum is not there. But then I move to the fourth layer, and you see, I see a lot of hafnium, little bit of titanium, and platinum a lot, because platinum is close to this. I get a signal from here. See, I acquire EDS spectrum from point to point. EDA spectrum will give you what elements are present in that particular region. From that, I can understand what my layers are. Why should I put these kind of many layers, to improve the dielectric constant of the material? See, this is a complete dielectric. When I put that, I'm expecting that if the dielectric constant will improve so that the capacitance of this MOS capacitor will increase. Okay, that's the whole idea. Okay, yeah. Yeah, this is something else. That's all. I mean, I guess I finish here. This is another analysis, which is not very much important for you, actually, yeah. Only thing I'll just complete with a little more, MOS in the recent technology, MOS was started with a simple MOS, but it was used along with MOSFET, actually, it's a P-type MOS or N-type MOS by having a channelier or CMOS complementary metal oxide semiconductors and metal insulator semiconductor MOSFET, all filled up, it's floating gate MOSFETs and thin film transistor TFTs, that's why we have all these LEDs and, all those screens, because of the thin film transistors and multi-gate field effect transistors and QFET quantum field effect transistors, which uses quantum tunneling. And these are the evolution of the MOSFETs to the recent technology, many types of FETs we are using in the recent electronics. And the important point of this is, people are now looking for the high dielectric constant material, which are called as the high K materials, as a substitute for silicon dioxide. Silicon dioxide is a very good material for mass capacitance. Okay. But it has, when you go to make it very thin, like 1 nanometer, it will become really leaky. Leakage current will be really large. So to avoid that leakage current, people are trying to replace this material by using high dielectric constant material, such as hafnium oxide, zirconium oxide, aluminum oxide, or combinations of them. Even tantalum oxide was tried, tantalum pentoxide, many oxides, by high dielectric constant oxides. These materials are the state-of-the-art materials which are looked for the applications in the mass capacitors. And similarly, the technology for fabricating them, they've gone to the sub-nanometer mode fabrication technology. Previously, if you want to have a channel, our gate oxide layer is about 1 nanometer. Now, if you want, you can make even a 0.5 nanometer layer by fabrication technology, which was improved a lot, actually. That's called as a sub-nanometer node fabrication. Okay, this technology was achieved in your VLSI technology. So the concentration of components that you can make per square millimeter, per square centimeter is enormously increased. So still miniaturization is highly possible there. And people are recently using normally the ALD, which is called as an atomic layer deposition, which is one of the deposition techniques. I did not mention there, but it's a very popular technique. Even if you want to coat one layer, which is called as a monolayer, you can coat this with high uniformity of the layer. That can be done by an atomic layer. And current state of the technology is to produce, the major portion of semiconductor, this is taken from the ITRS for devices and systems. That is the technology that people are looking for. The semiconductor device production is devoted digital logic that needs to support a technology platform for 2 device types. One is high performance logic devices with, but that should use low power but high density. Okay, so that is the one people are using for that. Key consideration for this technology platform are speed, power, density, and cost. The Moore roadmap, which is ITRS roadmap, which is, that's Moore was a scientist who made that, provides an enablement view for continued scaling of MOSFET in order to maintain historical trends of improved device performance at reduced cost. This is what you're going to look for that. Okay, high performance devices are low cost but with high power. That is the key technology that people are looking for that. With that, I would like to acknowledge the metal ceramic interface group at the Technion, because this is a place where I've done most of the work on this MOS capacitors. And I would like to thank one of my students, Dr. Uday Banu. Banu, he has done a lot of work on this device in our lab, and I want to do DST SCRB for the project that he has given to me, like, Young Scientist Award. I got the fast track project by which we have developed a thin film coating technology here. And whatever I have done here was because of the funding from the DST. So I would like to thank the DST India also. With that, I would like to complete my talk. And if you have any questions, I'm here. I'm sorry for going it really fast. I don't know any other way. So let me stop the sharing timing. Are you wanted to be seen? Yeah, well, let me see, because I don't see you, anybody. So if you have any questions, sir, please. Yes.
Sir, good evening, sir.
Yeah.
I'm Priyadarshini from Madras University.
Okay.
I have a question that why in the starting you told that most of the metal electrodes are heavily doped with polysilicon. Why it is so, sir?
Okay, because it was, they wanted to make the compatibility, because they don't want to have the, one moment, let me, do you see my presentation now? Yes. Let me open
Yes,
one empty slide. Insert slide. Yeah. So I can explain here. The idea is to reduce the work function difference between the silicon substrate and the, you have the silicon substrate here, and you have a metal, and you have a metal here, right? So they don't want to have much potential difference between them or work function difference between them. This is also silicon and this also silicon. So they wanted to use the same type of material to have the phi ms almost 0, which means like a flat band condition already. That's why they chose polysilicon, which was heavily doped, because the one was heavily doped with a N type, and it behaves like a semiconductor, behaves like a metal, but having the work function similar to silicon, so that the difference is almost 0. So they achieve flat band condition without applying any voltage. That's why they choose the polysilicon.
Okay, sir.
Is that okay? Yes.
So,
Yes, yes.
so is it possible to change the threshold voltage value, sir, by means of doping or any other way in order to get the depletion region at the second?
Of course, of course. For example, if this depletion layer is depending on the, anyway you have the silicon which is doped with a p-type silicon. So depending on the concentration of the silicon, also the material that you're using, you can use zirconium oxide or hafnium oxide. For that, if I fabricate one capacitor with, for example, hafnium oxide, which is one, type, and if I use the zirconium oxide in another type, so everything will have different work functions. So accordingly, your threshold voltage will be different for different materials. So obviously you can tune that. I mean, it will be different for different materials. We are not tuning them. We fabricate them and we study them. If you want to have a different threshold voltage, no, actually you don't need to literally tune the threshold voltage. Only thing you should know what is the threshold voltage. So you fabricate it and study that, and you get the threshold voltage from that. And threshold voltage will be obviously different for different systems that you can get from your CV measurement. Okay. In fact, you can tune if you want a different threshold voltage. Of course, you can change the silicon with a different doping, or you can change the material. Then it is a different capacitor, right? Different system. For a given system, I don't think that will change actually, for a given conditions. Okay.
Sir? Yes, sir. Thank you, sir.
Yeah.
Sir, you said that when the voltage applied is negative, then charges will be accumulated, and when the voltage applied is positive, then the a depletion layer will be formed.
Yeah.
My question is that when continuous varying voltage is applied,
Yeah.
will there be any condition when for the for the material to be damaged?
Yeah. See, any capacitor, as I said, you have this, let's say, usually you see a capacitor like this, correct? Two leads and the capacitance, for example, if 25 volt, 1000 microfarad, they put like this, this is what we call as a rating, okay? If you go, for example, we can see, I'll tell you that, okay? In this kind of capacitor, this capacitor can be charged by using only the 25 volt. That is the rating of this device, okay? What is the meaning? You have this, okay, every time, okay. I have two, this is a dielectric. This is one electrode and this is another electrode, okay? You're applying a potential here. See, this dielectric material has the ability to withstand the voltage to a certain level. Why? Because the distance is D and you're applying a potential V and the field will be developed, E is like V by D. When you bring it, for example, when you bring it a little closer, whatever it is, for any reason, if you apply heavy voltage, the field developed will developed in the material will be really high. So the material cannot withstand that strong field. So what will happen? The dielectric metal will not be behaving like a dielectric. It will break down. It's, that is called as a dielectric breakdown. It is really a physical damage, which means really blast. So if you have this capacitor, you can blast the capacitor. So you cannot keep on applying a voltage. Your operating voltage should be within the rating of this capacitor, okay? And if you want to, if you want to know the limit, you can do an IV characterization. IV characterization was like this, I have shown it. No, you can apply voltage, you can measure the current density here. Let me measure the J, current density. For the voltage that you are applying, it will be going smooth. When it breaks, it will be an immediate change will be there. Too much of current will be flowing through this, which means it's lost its behavior and all current will be flowing through that. So leakage current will be higher and this is called as a breakdown voltage. It's exactly this here. So you should not operate the voltage beyond that breakdown voltage. Every capacitor has the breakdown voltage depending on the dielectric that is being used in that. You cannot apply too much voltage beyond the limit. Okay?
Thank you, sir.
Yes.
Sir, thank you for this informative session, sir.
Yes.
In one case, you mentioned that when we heat it at 1000 degrees Celsius, the metal, when it is amorphous, it turns into crystalline. Why is it so, sir?
That is a regular, okay, that is the dynamics of crystal growth. You have, let's say I'm just drawing a box. I'm a bad drawer, but still. You say you have atoms, you have atoms randomly arranged, okay? When you apply a heat, okay, the system is acquiring a heat and trying to order themselves. It will be taken to a high temperature state, which is like a non-equilibrium state. Then you cool this, okay? Before applying this kind of temperature, normally, when you apply heat to the system, it will, if it is an amorphous state, it will try to achieve an equilibrium state. Because if any crystal is present in an amorphous state, which is called as a high energy state, okay, it's a non-equilibrium state, but it cannot move by itself. Let me say one example here by saying, you might have traveled a lot in your Pallavan, PRTC or Chennai bus, let's say, right? Okay. You see, you have some number of seats and some number of people who are standing in that. See, people who are sitting in the seat, they are very stable, right? They sit comfortably. But people who are in the middle standing, they are not in a stable state, correct? They will be moving here and there and they will feel congested. Similarly, the point is that people who are in the seat is arranged, ordered way, and they feel very comfort. That's an equilibrium state. But people who are in the middle, they're in non-equilibrium state. Let's say 2 people get down from the seat. Immediately the non-equilibrium state, these people who are in the standing, they'll go and occupy that, correct? To do that, some people have to get down. That's taking place by an external something, correct? Similarly, here the atoms are arranged in a random way, which is a non-equilibrium state. So it is interested to go to a crystalline state, which is an ordered state where atoms are arranged in an ordered way. Okay, but that cannot happen naturally. So it needs some energy to happen. For that, you need to apply some type of energy. Here we apply through heat. It can be 1000 degrees centigrade, maybe 500, 600, depends on the heat. So then, this material will start to move, and when it wants to arrange again, it will not arrange in the same way as it was, because that was a non-equilibrium state. It will arrange in a first state, then naturally, by following a symmetry, that a next atom will be forming next to that. It is a kind of crystal growth. The crystal will start to grow by following a natural law, which is a thermodynamically very stable state. Then the crystallization will occur. Okay, so non-equilibrium state to an equilibrium state will be happening there. So that's what the crystallization, that is a phenomenon of crystallization, completely different from what we study here. But that's a complete different thermodynamics. So all non-equilibrium objects will try to convert themselves into an equilibrium state. Here that equilibrium state is associated or assisted by a temperature. That's what is exactly happening. Okay. You can study about crystallization. That gives you more idea about this.
Yes, sir. Thank you.
Okay. Yeah. Any other questions?
Sir, good evening, sir.
Yes.
So what are the advantages of MIM capacitors over MOS capacitors, sir?
I don't think that is any great advantage. Only thing is that, people have attempted many types. Only difference is this. Actually, I would say that, again, people wanted to try the same metal here. For example, you have a silicon substrate. In MIM capacitor, you literally don't need a silicon substrate. But they wanted to have another coat here, metal layer, and they take a contact from here. And they have an oxide layer, another metal layer on that. So this is a metal insulator metal. Okay. Here the job of silicon is just a silicon, substrate. It does not have any interface with them. So there is no interface dynamics now. So the complete charge, distribution will be completely different here, because you don't have the contribution of silicon anywhere here. You study only this region. So metal insulator and metal insulator. There is no silicon here. So there is no semiconductor state. It's completely a different system, and it will be studied completely differently. I don't think that we should compare that with the metal oxide semiconductor, because semiconductor makes an interface here with, but here it's not. So it is a completely different system. I think that it is behaving like a regular capacitor. Based on its CV and IV characteristics, might be, concluded to be preferred or not preferred. I'm not sure. But still, the technology people are following the MOS better, because silicon makes an interface. That is a well understood phenomena, and people follow that. Other than that, I don't think that the great difference is there. It is completely different. I don't think that we should compare that.
Okay, sir. Thank you, sir.
Yeah.
Sir?
Yes.
Sir, how to prevent?
Yeah. Yes. I'm able to.
Sir, how to prevent or overcome the voltage current leakage in capacitors, sir?
Yeah. See. Yeah. That is why all these attempts were done. Actually, it should be done by research. When you go a thin layer underneath, you see, that is what exactly happening. Previously, all these MOS capacitors was used to fabricate with SiO2. Okay. But now miniaturization is to be done. If you want to coat MOS, silicon oxide, it has to be few nanometers or few tens of nanometers. maybe 10 nanometer, 20 nanometer. Now one capacitor I've shown was 90 nanometer thick. So when you want to make more components in less area, that's what we call as a miniaturization. This thickness has to be reduced. So when you want to use the same material, silicon dioxide, it will be leaky. That cannot be controlled because that's the nature of the silicon dioxide. So that is why people were looking for different combinations of the materials, like the high dielectric constant materials. You know, why we want to use the high dielectric constant materials? You know, this material can be, this material has high dielectric constant, so high capacitance naturally. So the capacitance is not compromised. Because of its high dielectric constant compared to silicon dioxide's dielectric constant is 3.4, I think, about 3.4. If you take hafnium oxide, it can go even 30 dielectric constant. Because of the huge high dielectric constant, you can coat, very thin film of hafnium oxide. For example, you can coat 1 nanometer of hafnium oxide. This will behave like 10 nanometer of silicon dioxide. They define this as equivalent oxide thickness, EOT. Okay, so physically, which is like 1 nanometer, the physical dimension of the material, the device will be reduced, but it is equivalent to 10 nanometer of this silicon dioxide. So you know, this thickness is reduced, but work like 10 nanometer, equivalent oxide thickness. Okay, so this is how, I mean, which means you're not reducing the leakage of this, but you change the material, you reduce the leakage. You achieve the lower thickness as 1 nanometer, that is what you want. But you know, the leakage is less because that is the behavior of the hafnium oxide. You cannot tell the hafnium oxide to leak this much of current because hafnium oxide is hafnium oxide. But my idea is to make, disguise, it's like replacing one with other, but performing much better than this. So 1 nanometer is behaving like 10 nanometer of silicon dioxide. But 1 nanometer is the physical thickness I quoted, work like this. So this is how I can, if hafnium oxide is not interesting, hafnium oxide is good actually. Many people are doing research on different types of materials with very less leakage current. They quote this and make a MOS and measure the IV, and they will say, okay, what is leakage current? Let's say femto ampere, or nanoampere, picoampere, whatever it is. And there are many attempts were made. People have made a hafnium oxide layer, or let's say oxide layer, and put metals inside. Metal nanoparticle inside. When you have a metal nanoparticle, they have the positive charges and all these charges which will be trapped here are negative charges. This metal nanoparticle in the oxide will act as a charge trapping centers. So they will behave like a mini capacitor. When you have a charge, when you have a charge layer inside, the outside you have another charge, opposite charge. So they will behave like a mini capacitor. So they put metal nanoparticle in the oxide layer to increase the capacitance and to avoid the leakage current. Which means they increase the capacitance, which means that it will be a lower leakage current. So the people have attempted many types. And I have shown you a capacitor with many layers, like this. Like this, see? So this is also an attempt to avoid the leakage current. The ultimate aim is to get high dielectric constant, low leakage current density. These are the two major objectives of fabricating the device. So accordingly, all your materials will be, changed, or, you can put in another material, various combinations just to try, and you try to get the best one, okay? And many of them have been attempted in the literature, by people, okay?
Okay, sir. Thank you, sir.
Yeah. Any other question, guys?
Senior, please check your chat box. I think a couple of students posted some questions in your chat box.
Okay.
Mic issue students may generally.
Okay. One question is, in case of p-type, if you take n-type semiconductor, what change happens? It just a reverse actually. That's a good question actually. I'll tell you that. You see, let me go to that and I can tell you exactly. See, he was asking, yeah, let me be here on this. See, he was asking me, instead of p-type silicon, if I put n-type silicon, what will happen? Here, if I put n-type silicon, so this curve will be completely reversed. You know, you get, let me draw here. Let me draw here. Maybe I'll change the ink color so that you can see it. You know, it is like asking, what is the charge of electrons? It's positive. It's negative, right?
Negative.
Yes.
Yeah. I'm telling you, I want to give a charge for the electron as positive. What will happen? Anything will happen? No. No, charge is an attribute, right? Whatever is the charge, it will be now. If you put wherever you want to put electrons, then you need to replace electrons by holes and holes by electrons. Nothing will change. Similarly, if I put positive here and you know, p silicon, if I replace it by n silicon, the whole thing will be just a reverse actually. You know, my accumulation will start here and your depletion will start here and your inversion will take place here. This is the high frequency. Here again it will be the accumulation, depletion, and your inversion. Inversion will take place here, and that will be reverse. Nothing will change. Everything else will be the same. Okay, that is one question. And somebody asked me, sir, could you please, when V is much greater than 0 gain? Yeah, that is the situation here. See, when V is much greater than 0, which is really high voltage, see, there are two things occurs here. One is a high frequency. Now, one thing let me do that. I'll delete all these writing, then I'll come back. Okay, because this guy. Let me do those things. Yeah, I'll delete and I'll come fresh. Yeah. Okay, so look at this actually. You know, this case is clear, right? And this case is a depletion. That you understand, correct? These two cases are clear, I believe, because of your question. So let me talk about this. Yes. See, I apply heavy voltage. Naturally, when I apply a light voltage, you know, very easy way also you can see that. When I apply a plus voltage, which is small in magnitude, I develop a region here, okay, which is called as a depletion region. Depletion region, what is the meaning of depletion? Depletion is the void of that. Charges are not there. See, when I apply positive here, naturally in this area, I will develop a negative here, right? Develop here on that side. It's like a capacitor drawing. When you develop a negative there, equivalently you develop a positive here. Or you can take the other way also, doesn't matter, okay? Because it's a oxide, so oxide will polarize. That's why I'm writing here. When you apply a positive voltage, negative charges will be accumulated here, positive charges will be accumulated here. But net charge, if you calculate, it will be 0, but accumulated here on this. See, this positive charge will push them away because they are the same charges, will repel each other, so that this will push them. That's why this depletion region is developed here. So the thickness will be, you can say that, you know, maybe some T depletion, you can put that. That's the thickness of that. Okay. So that is one case, that's depletion exactly happening here. So there are two capacitance will be developed, C0 and CS. They are in series, but the control is taken over by this CS, which is small in quantity or magnitude. So when you increase the voltage, this thickness will increase, and that increase will reduce the capacitance of CS. So that is why the total capacitance will decrease in the depletion region here, okay? So you are increasing the voltage again further. Now, what will happen? Not just this depletion takes place, okay? The first thing is that because of the heavy positive voltage, the thickness of the layer will be really high. Okay, but that is normally happening there. Okay, so when that happens, in addition to that, because the heavy voltage, heavy field will be set up there, electric field, and that heavy field will make an instability in the semiconductor, and that develops, that's called as a thermal electrons. It will generate thermal electrons. Thermal electrons will be generated by jumping of this electron to the conduction band. If this is a conduction band, this is valence band. So it will develop positive holes and negative charges here. This negative charge comes here, and this positive holes will go to this charges, it will be pushed here. So that will be happening there. Okay. So in this case, in the high voltage side, there is another phenomena which is to be taken care, which is a time constant. This thermal electrons are to be generated, and these thermal electrons are just making a small layer here, which means that is supposed to be positive, but because of the thermal electrons, it is converted into a negative. You see, that is called as an inversion layer. Inversion is generated. So the capacitance, because of the wide, the contribution of the capacitance will also become like negligible. Then it will be like total capacitance is just managed by this C ox again. It will go back to this case here. This is happening when you change your voltage with a low frequency, which is like 10 hertz. You are applying an oscillating field there, oscillating voltage here. This occurs at low voltage, but if you apply a heavy, high frequency voltage here, there are two cases. Okay, one is low frequency. When you low frequency, that becomes like exact inversion, and inversion stays as such. It will be happening there continuously because you are changing the voltage here, which gives enough time for this charge carriers are to be developed and inversion to take place. But if you apply a high frequency voltage, there is no time for this to take place, because before this is taking place and being pulled away to the sides, another negative charge will come place. So that will be like a switching of field very faster, and that will not allow this to happen, and inversion will not be inversion. There won't be a strong inversion layer there. That will be just like a depletion layer. So this will continues to stay with this layer. So it will be called as a weak inversion layer. There won't be a strong inversion layer. That will occur only at high frequency voltage, high frequency region. Okay, this is called as a C minimum. Here it is called as a C maximum. So when you apply high voltage, there are two cases: low frequency voltage, high frequency voltage. Low frequency will behave this way. This is an ideal case when you have a high frequency and this stays in a low capacitance region, and that will be the another case. Is it clear? Man, I don't know his name. I believe it's okay. Yeah. So, someone was asking what are the factors that affect the flat band voltage. If you look at the flat band voltage is a voltage which keeps the voltage flat. Okay. As long as you do not have any charges inside the oxide layer, also the semiconductor layer, the flat band voltage stays zero actually. Okay. So it won't happen. If you develop, or because of your work function difference, there are any charges developed in between, then its flat band voltage will be affected. So the flat band voltage is affected just because of the different types of charges packed or trapped at the interface and the oxides, all charges together. That will disturb the flat band voltage. So in case if the band is bends because of the charges present there, then we have to apply a voltage to correct it. Okay, to make the band flat. That voltage we'll be calling it as a flat band voltage. In an ideal system, flat band voltage will be zero, where no charges are trapped in oxide or in a semiconductor as well. Okay, so whatever if there is a charge imbalance or charge distribution changes, that will disturb the flat band voltage. Okay, that was one question. Okay, What is the temperature withstanding capacity of this MOS capacitor? As we know, in case of semiconductor, the resistance decreases with increase in temperature. Whether this has any effect over the capacitor. Okay, as I told you, a temperature, a temperature, yes. Okay, temperature we have to discuss in terms of the temperature in the dielectric. Okay, temperature in the dielectric. Of course, of course, the resistivity, conductivity of the silicon will be changing with your statement, because that is the semiconductor material. Okay, but we need to look at the temperature variation with respect to the dielectric. When you apply temperature, obviously the conductivity of the layer will be increasing, because it is also behaving in a semiconductor nature. We do not want that. We want the dielectric to be perfectly an insulating material. Okay, we do not want that to be conducting. If you increase the temperature, and you know that what happens exactly the same thing what happens in the semiconductor will happen here. The conductivity will slightly increase because of the band. You increase you put a more energy, so the electrons will jump into the conduction band. It will try to conduct. So I don't want this to be conducted. So if you increase the temperature, obviously the capacitance will be dying. So we don't want that to happen. So that is the effect, I would say that. Okay, we don't want to increase the temperature. Any other questions? That's all in the chat box. I think it's quite good, huh? Very interactive group, by the way. That's nice. I did not expect that many questions from you guys. Very nice. Yes.
We may close the session now. Okay.
Okay. Yes.
So I thank you for your wonderful presentation, also for interacting with our students. Students, I'm going to request Dr. Thangadurai to stop the session. Is it okay for you?
Yes, sir.
Okay.
Yes.
Also, if you have any questions, you can email me. I will try to answer. I would also say that your organizer Prakash is much stronger in this subject than me. I would tell you that he can clarify most of the things. I would say that, but still, if you have any questions, you can email me or you can talk to him also. He is exactly working on this recently. I started working on it quite a long time ago, but one of my PhD students have done the job and he left now. But we little bit diverted our direction to the other research. But anyway, I'm really happy to recollect all my knowledge on that, and I myself refreshed. I'm happy to share with you, and I thought, he was already telling me that they'll be asking questions in between, but it's fantastic session that I had, and you're really nice, interactive people, and I'm really happy to be a part of that. I thank you also, Dr. Prakash, for the opportunity.
Thanks for your presentation and wonderful interaction with our students. Thank you very much.
Yeah, thank you guys.